Okay, I've got 5 examples of rolling stuff for you guys. So let's just get to it here. So the first example is we've got a ramp. It's inclined at 30 degrees. We've got a ball here at the top. Some distance, this is 3 meters. And then it's going to roll off it, and it's obviously going to hit some point down here. Okay, oops. That may not have been totally obvious from the wording there, but hopefully it makes sense now that the ball's going to roll down and then go flying off, and then it's going to hit the ground. Okay. So hopefully you recognize this from some of our other work, that this is obviously a 2-part problem, right? We've got the rolling part, and then we've got the flying through the air part. So let's start with the rolling part, right? So this is the rolling part. Okay. And we're concerned with it's fully rolling, right? Anytime you say rolling, you should assume it's fully rolling. And we're concerned with the velocities. So we don't need to do force. We can do energy. So this is going to be, right, kinetic energy initial plus potential energy initial, right, equals, sorry, I do PE for core, or for regular physics, not for you guys, because U seems weird to them. U initial equals K final, U final. There's no non-conservative work because it's fully rolling. And so I have 0 equals, or not equals, 0 plus 3 times 9.8 times height of 3, another 3, equals, and here's the fun part. We have 1/2 3 v squared, plus we have the rotational kinetic energy, so 1/2, it's going to be I omega squared. Okay. And then there's going to be plus 0. So first thing, we should probably figure out what omega is, or what I is. So for a ball, right, it is 2/5 mr squared. This is 2/5 times the mass times 0.2. Actually, I'm going to leave this as r. You'll see in a second why. I'm going to leave it as 3 too. So I'm actually not going to multiply that out. All right, so I've got 3 times 29.4 equals 1/2 times 3 times v squared, 1/2 times 2/5 times 3 r squared omega squared. So good. The reason I left those 3's there is, right, is because they're going to cancel out nicely enough. I got 3. Oops. I really want to do that in a different color. My 3 are going to cancel out. So 29.4 is equal to 1/2 v squared plus 1/5 r squared omega squared. Now, this is omega. We know that v, when rolling, v com equals v tangential, which is equal, right, to omega r. So omega is equal to v com over r. So I plug that in here and I get 29.4 equals 1/2 v squared plus 1/5 r squared v squared over r squared. So I get to cancel out those r's, and I realize that should be 1/5, not 1/2. And this is going to become 7/10 v squared. And we're going to get that v is equal to 5 or 6.48. Okay. And this is, right, it's at that angle. So now we have to do 2D kinematics. So we have v initial x equals 6.4. 6.48 cosine of 30. V initial y equals 6.48 times sine of 30. And I guess I should say this is down, so -1. I probably should just, actually I'll just make it negative to begin with. I think I'm doing this the hard way. Right? AY equals -9.8. Change in y equals -2, right? Because this is 2 meters. I figure out I'm gonna skip ahead. So time then is equal to 0.389 seconds if we do the kinematics, which means that change in x is equal to 2.18 meters. Okay, so 2 parts, but we use the energy conservation to get the velocity at the bottom. All right, so this was a simple energy one, right? This is energy where it's rolling and sliding. Okay, this is a little more complicated. And I've got 2 examples of that just to try and help us figure anything out. So we got sliding. So it starts out sliding. Right, so we got some velocity. And we've got friction on this. So let's look at the forces here. So first thing, we've got Fg. Right, we do have normal force. And finally we have friction. This point right here is moving to the right. Therefore the friction at that point is to the left. Now, one of the things you have to do is we need to align positive directions here. So let's say if we're going to say to the right is positive, then when it's moving to the right, it's also rolling clockwise. So we're also going to say that clockwise is positive. Okay, just this time. So now what I do is I need to set up F net equation. F net equals negative force of kinetic friction is in the x direction, which is mg uk. Negative mg uk, which means that acceleration is going to equal negative g uk, or negative 4.9. I also need a torque net equation. Okay, now the net torque here, force of gravity is straight down, but it's the radius is right. This would be the torque of gravity plus the torque of the normal force plus the torque of friction. Torque of gravity has a radius of 0. The gravity acts at the center. Okay, torque of normal force has an angle of 180 degrees, right? Because the radial vector is straight down, and the normal force is actually pointing straight back towards the center. So it's 180 degrees. So neither of these are going to make it rotate. Okay, so my torque net, which is I alpha, equals R cross force of friction. All right. So I, right, this is a thin hoop, so this is m r squared alpha equals R, and the force of friction, right, is still going to be mg uk, right? And this is going to be sine of 90, right? The r vector is straight down. Again, if we're looking at this object, the force of friction is this way, and the r vector is this way. Okay. So we can cancel out a bunch of stuff here. Mass, 1r, 1r. And we can go ahead and we can solve that. Alpha, this is 0.25 alpha equals 4.9. Is that all this? Yeah, 4.9. Which means that alpha is equal to 19.6. Oh, I should mention the force of friction, the torque is positive because this is going to make it go right clockwise. This friction, this torque, right? And we assign that to be positive direction. All right, so now we get to why this matters. So the main thing for fully rolling, right, means that right. So I want to end at that point. So what I want is V final to equal R omega final. Well, how can I do that? Well, I can say, well, V final equals V initial plus AT. So V final equals 10 minus 4.9 T. I've also got that omega final equals omega initial plus alpha T, which is 0 plus 19.6 T. I can plug those in here. So I've got 10 minus 4.9 T equals 0.25 times 19.6 T. Okay. And I can solve for T here, and I should get a time of 1.02 seconds. That's how long it moves before it becomes fully rolling. Once I have time, it's pretty easy to go back and find change in x. Change in x equals v initial times time plus 1/2 at squared. And I would do that, and I would actually solve that out, but I actually forgot to calculate that ahead of time. So we're going to leave that right there. Sorry about that. Yeah, I'm going to leave that there. Okay, but that's what you would do. Always find time first. Also, please note that alpha and A are not related. You can't do, right? When it's rolling and sliding, you can't say that alpha equals, or A equals R alpha, and that's because it's not fully rolling. All right. So this time we've got a ball. Let's say it's spinning that way. Okay. With an omega equals 30, and it's set down on top of this object here. So when it's set down, this point right here, this point is going to have a tangential velocity. And in fact, the v column is 0, so we can even say the linear velocity, right, is that way, which means that the force of friction is going to oppose that direction. So the force of friction is that way. Okay, so it's important to note that. I also should say that we should again pick, and this time I'm going to go the other way. I'm going to say this way is positive, and that way is positive. So left and counterclockwise are positive. I want to know what its velocity is going to be when it starts fully rolling. Same idea here. I need F net equation. F net is going to equal force of friction, which is, or F net x at least. Again, the vertical stuff's canceling out, so hopefully that's not going to be an issue right here. So this is 0.5 kilograms times 0.3 times 9.8. This is, right, so it's 0.5, 9.8 times 0.3. .94. Oh, that's newtons. Actually, it's that's wrong. Sorry, y'all, that's wrong. It's 1.47. Then the acceleration is 2.94. Okay. So then we do torque net, right? Equals, and again, torque of normal force, torque of gravity are going to be this. So torque of friction, which is R cross force of friction, which is going to be 0.1 times force of friction, which is 1.47. And it's going to be times sine of 90, right? And it's also going to be times -1, right? Because this whole thing, right, if we look at this object, the force of friction is this way. It's going to make it turn in a negative direction. So then I have I alpha equals 0.147 or negative 0.147, and I, this is a ball, so this is 2/5 mr squared alpha equals negative 0.147. And if you do this out, plug everything in, you get alpha is going to be negative 73.5. That seems really high, but angular accelerations can be quite high in a problem like this because the friction, because it's got its moment of inertia is really small. I didn't know, we didn't actually calculate it out, but right, this is 2/5 mr squared. R squared is 0.1, so that's 0.01. 0.5. So 1/5 times 0.01. It's a really tiny moment of inertia. So it's pretty cool. So then we get, right, we go that omega final equals omega initial plus alpha t, which is 30 minus 73.5 t, and v final equals 0 plus 2.94 t. And I say that omega final, or v final, equals omega final times r. So 2.94 t equals 30 minus 73.5 t times r, which is 0.1. We can solve for t equals 0.29 seconds. So it doesn't take long for it to start fully rolling. It's pretty fast. And what that means is omega final, or not omega final. I asked for final velocity, not omega. I go back to it right here, and I can figure out that if I plug this back in, right, that v final is 0.853 meters per second. Okay. The yo-yo problems. These are some of my favorite things because they're just like so different from what you expect. Make that a little smaller, give myself a little more room to work here. So we got a yo-yo. The two discs part is not something you should be paying very close attention to. The two discs, right, because the yo-yo just has like a break in the middle, so the two discs, you can treat them as if they're one disc. That's just got the total mass of 0.05, right? So you've got this disc, and you've got a little axis in the middle, and the rope is acting right here. And that's the tension in the rope, right? And the only other force on this thing is you've got Fg. Now, because this is an acceleration problem, it's also a situation where there's another force that's not just gravity. So we have to do this with force and torque. Now, this is a fully rolling problem. It's rolling along the string. Right? It's rolling along the string. It's not slipping along the string, which means that this is a radius of 0.3 centimeters, which means that V is equal to 0.03 omega, and A is equal to 0.03 alpha. Okay, so I just want to be careful. These things are both true. It's fully rolling. Let's go to the force question. Oh, and I need to do things. So I'm going to say down is positive, and because when it's going down, it's going to spin counterclockwise, I'm going to say that counterclockwise is positive. Okay? So F net equals Fg minus torque, or minus the tension, not torque. That's a very much a normal T. So this is 0.05 A equals 0.05 times 9.8 minus the tension. We don't know what that tension is. However, torque net is going to be equal to R cross Fg plus R cross tension. The R for Fg, this R, that R is 0. So I've got I alpha equals R, which is 0.03, times the tension. And again, it's 90 degrees times sine of 90. And I got to check to make sure, like, is this tension going to be making it spin left or clockwise or counterclockwise? It's going to make it spinning positive, so we'll keep it that way. So this becomes I. Oh, I made a mistake, small mistake. It's these ones. I was using the wrong value up here. These are 0.002 omega, 0.002 alpha. Okay, and this R right here, this is also 0.002, right? Because it's the 0.03 is this radius. I want just the radius, just the little axle. So 0.002. All right, my bad. So I, it's a disk, so this is 1/2 times 0.05 times 0.03 squared. I'm not sure I wrote down what that was. Yeah, I didn't. Plugging all that in. Okay. So this is still true. This is going to be, right, 1/2 still times 0.05 times 0.03 squared equals 0.002 t. All right, if you do this, you get that t. Oop, I need an alpha. You should get this. This is, and then I'm going to put in. Oh yeah, and then I'm going to put in that a. Right, this alpha becomes a. So this is 1/2 times 0.05, 0.03 squared times alpha, which is a over 0.02. T. It should be a capital T. Okay, and I do this, you get T is equal to 5.625 A. And then you can plug that back in over here. This is 0.05 A, 0.05, 9.8 minus 5.625 A. Do that out, you get A equals alright, I actually can't read my own handwriting. 0.0. I think this is 8.6. I think it's 8.6. Okay, don't 100% quote me on that, but that's the acceleration. Whew. All right, final one here. Okay, we got a cylinder, radius 1.1 meter, and a mass of 2 kilograms. It has a terminal axis that is half the radius. So and I want to be clear, there's actually 2 possible outcomes to this. I'd be like, why are there 2? Well, in one situation, the string is pulling like that. In another situation, the string is pulling from underneath. Okay. All right, so you got this thing here, right? In the last problem, we knew the direction of all the forces. In this case, we actually don't know the force of friction on the cylinder. We don't know what direction it is to me. Is it like preventing it from turning, but it's also making it go? Like, I don't know. Is it preventing it from turning? Hard to say. On these problems, you can just randomly pick a direction for the force of friction. In both cases, I'm going to pick this way. If you are wrong, all that will happen is you will get a negative value for it. And you'll be like, oh, I was wrong. Cool, no big deal. Now remember, these are both fully rolling, so we can still do that. Vcom equal to omega r, and acom is equal to alpha times r. So both those things are still true. We could also do that I equals 1/2 times 2 times 0.1 squared, which is 0.01. So our i's are both 0.01 for both situations. Last thing we need to do, I'm going to say that to the right is positive. And I'm going to go and right, and that means that this direction clockwise is positive. All right, so for the first one here, F net equals the force of friction plus tension. Okay? That means that 2A is force of friction plus 5. Now you might be wondering, why don't I just plug in, I don't need a coefficient of friction. This is static friction. It's not sliding. So because it's static friction, this friction could be anything as long as it's not sliding. We don't know what it is. Okay, I also need torque. Torque net is equal to torque of the tension plus torque of friction. Okay, so this is I alpha R cross tension plus R cross force of friction. So I alpha, this is 0.01. I can go and put this in. This is going to be A over 0.1 is equal to 0.1. The tension is going to make it spin clockwise. So it's going to be positive. It's 90 degrees. 0.1 t plus r 0.1 times the force of friction. It's time that the force of friction is going to make it spin the other way. If I solve this out, I get that this is 0.1a equals 0.1 t minus 0.1 force of friction, which means that a is equal to t minus force of friction. Actually, I know what t is this whole time. It's a equals 5 minus the force of friction. I can go plug this back in up here, and in fact I'm going to do it the other way. I'm going to do force of friction equals 5 minus a. Plug that back in, right, and I get 2a equals 5 minus a plus 5. 3a equals 10. I have made a mistake. This value right here, the tension is at a radius of 0.05 and the force of friction is at 1. So this is 0.05, which means that this is 0.05, which means this is 0.5, yeah, t over 2, which means 2.5, 2.5, 2.5, 2.5, 2.5. Actually, that's still 5. No, it's 2.5. Yeah, so 2.5. Yeah, sorry, got distracted there. This is 7.5. A equals 2.5. And I've made a mistake there as well. Delightful. What did I do? So the acceleration can't be 2.5 because that would be if it was just sliding. So I've made a mistake. And the question is why? How have I made this mistake? 0.05 times t. 0.1. Alright, well I'm not remaking this video at the moment, so I'm going to keep going. I'm going to do the second one, and hopefully I won't make the same mistake here. So this one, F net equals force of friction plus tension still. They're both to the right, but where torque is, it's a little bit different. So this is still 2a equals force of friction plus 5. Oh, I guess I should go back to the following force of friction here. 2.5 minus a, that would be a force of friction of 0. That's how I know I was wrong, because if there was no... Actually, I take it back. That's correct. It's possible for force of friction to be 0. Huh. I didn't mean to pick one where that was true. You'll see it's not true in this case. Force of friction being 0 means that the torque is being perfectly... That's because the radius is exactly half, and the I is exactly half of... and the I is the 1 for x is 1/2. So actually that works out. The force of friction being 0 for this one makes sense. Because the torque is what's made, the tension's enough to make it spin at exactly the same rate as it's moving. That actually makes sense. Okay. All right. That's true. Torque net in this case though is still torque tension plus torque of friction. I alpha r cross t plus r cross force of friction. But in this case, they're both negative. They're both trying to make it spin counterclockwise. Okay, So I alpha is going to be I is 0.01, and alpha is A over R, right? This is A over 0.1, because that's where it's rolling and turning on, right? So that's that point. That's the tangential distance. Okay, and this is going to be negative 0.05 t minus 0.1 force of friction. Multiply both sides by, so this is 0.1 A equals negative 0.05 t minus 0.1 force of friction. Divide that out, we get acceleration is negative 0.05 t minus 0.1 force of friction, right? And actually, I know what that is. This is negative 0.25 minus 0.1 force of friction. No, it's not, because we just multiplied out by that. I forgot to multiply out all that stuff. I just rewrote exactly what I had before. Whew. This becomes negative 0.5 t minus force of friction. This becomes negative, when we plug that in, it's negative 2.5 minus force of friction. A is. I can go back up here. Our force of friction, I guess, is negative A minus 2.5. I can plug that in up here. So I get 2A equals negative A minus 2.5 plus 5. 3A equals 2.5. A equals 0.833. If A is 0.833, then friction, right, is negative of that. So friction is negative 3.33. So friction is actually going back the other way, and that's totally fine. All right.